Hello, this is Will Salisbury and Chris Mutzel, and this is a video demonstrating our client-side peak shaving system with lithium iron phosphate batteries for Tufts University Spring Senior Design Project 2012. In this video, we will discuss our project goals, backgrounds and reasons for peak shaving, our project scope, the results from our fall proof of concept, the architecture and design of our final prototype, and the prototype results. The goal of this project was to build a physical prototype demonstrating peak shaving using lithium iron phosphate batteries for spark plug power. This task required study and development of relevant battery management techniques and battery dispatch logic. To dispatch batteries correctly, it is also necessary to develop methods for predicting electrical loads of a customer given a historical data set. Among other criteria, we determined success to be demonstrating the reduction of peak demand with a historical data set to within 10% of a new threshold found previously in an offline manner. This test was to be performed entirely within the functionality of the realized prototype by April 24, 2012. We are working with Sparkplug Power, a Boston-based startup, to implement demand-side peak shaving with lithium-ion batteries. Peak shaving is a strategy to reduce energy bills for commercial clients. These energy consumers, ranging from coffee houses to office buildings, are charged for the total energy they use and the highest amount of power they demand during the billing period. Energy costs can be reduced by storing energy at night when there is no demand charge, then offsetting the total amount of energy demanded from the utility during the day with this stored energy. The scope of our project was mainly limited to safety concerns, the cost of the components, and the availability of test equipment. The maximum power dissipated by the load in our prototype system was limited to 12 watts, approximately 1 amp at 12 volts. This voltage level allowed our project to be tested using standard oscilloscopes, multimeters, and function generators available in the engineering laboratory facilities. Not only would higher system terminal values require more robust equipment for testing, but the cost of the project would also be drastically increased. An example of the cost increase is shown on this slide. In addition, the need for current protection devices such as relays and fuses when working over 1 amp would also increase the complexity of the project. 6 lithium iron cells were arranged in series for a nominal stack voltage of 19.8 volts. This series configuration gave the stack capacity 2.5 amp hours at their nominal voltage. At a maximum current and voltage specified above, rough calculations show that the battery stack could be drained from 100% state of charge to zero in approximately 3.8 hours. The figure on this page displays the results for our step-ahead prediction using neural networks. The predicted value is shown in red. It can be seen that very low error prediction was obtained while using a single hidden layer, 15 nodes, and 4 months of historical data for training. Client-side load prediction is performed using artificial neural networks. This mathematical construct allows for pattern recognition and time series prediction of samples in a dataset. These networks are modeled by a series of hidden layers with a specified number of nodes. An input vector is applied at the input layer, multiplied by the weights of a hidden node, and summed to create an output vector. Our system is trained and predicts on historical data recorded by a real customer. The input vector is a series of delayed electrical loads. To aid in the network configuration process, a MATLAB script was created which found an optical prediction model for an input dataset by varying these parameters. In addition, autocorrelation of the historical data also enabled the determination of network inputs as predictors for low error outputs. Test. Using the step-ahead load prediction, we were then able to simulate peak shaving in MATLAB. As can be seen in the figure to the right, the peak demand of the customer is limited to a new threshold. This is done by allocating some amount of battery power at each time step. To model the high discharge rate of lithium iron phosphate chemistry, the battery stack is allowed near infinite discharge rate, meaning that it can provide any amount of power in a time step, assuming the battery has that much power to provide. Using our bounded battery simulation, we are able to determine the optimal threshold to which peak demand for a customer should be reduced. This is done by calculating future possible savings given a battery size. Some of the inputs for the optimization methods are the electricity prices and battery lifetime. In the figure to the right, it can be seen that the optimal threshold is above the minimum one for a given battery size. This makes sense because constant use of battery will quickly deplete its ability to hold charge, thus reducing the number of billing periods the system can be used for. The implemented prototype relies on MATLAB running on a personal computer for all load predictions, battery dispatch logic, and system monitoring and control. Test 2. The battery management system provides high-precision analog-to-digital conversions for the voltages and temperatures of the battery stack. This information is passed to the MATLAB simulation script for charge and discharge logic and monitoring. A TI evaluation module was used to fulfill the needs of the battery management system. The charge controller unit of our system is implemented using a TI evaluation module. The board contains a switched mode battery charge controller with constant frequency, synchronous PWM, and high accurate charge status monitoring. The power electronics unit is responsible for all DC level conversion, control of power used by the load, and the combination of grid and battery power. Because of the range of voltages of the battery stack, DC to DC conversion is an important part of the battery storage concept. In the prototype, power is drawn from a wall adapter. For concerns over safety and project scope, the maximum voltage is limited to 24 volts DC and the current to 2.5 amps. The power to the load, the battery, and the grid are all regulated to 12 volts DC. Because of the need for wire-level signals to control the various embedded units of the prototype, a microcontroller is used for communications purposes. Figure 5 shows the signaling schemes between the various devices. Variable passing between MATLAB and the microcontroller is performed over USB. The BMS, charge controller, and power electronics are connected to the system using 0 to 5 volt TTL logical signals, serial peripheral interface, and pulse width modulation, respectively. This picture shows the completed prototype. Clockwise from top left are the TI charge controller, lithium iron phosphate cells from A123, power electronics, Arduino microcontroller, and TI BMS. The central controller is implemented in software on a separate computer and is not shown. The simulation results shown in the figure here show the dispatch of power from the batteries during the course of 3 days. The total area under the load represents the total energy used by the customer. The blue represents power drawn from the grid, while the green arrow represents power drawn from the batteries to meet that load. The threshold in the simulation was fixed at 50% of the maximum client-side demand in the data, which occurs during the first day of this simulation. With our prototype, we were able to reduce peak load in the simulation dataset to within 10% of the new threshold. The implemented battery dispatch logic allowed the battery voltages, shown bottom right, to maintain near full charge while reducing the peaks to the lower threshold. While our power electronics lacked closed-loop control, our prototype results reflect accurate power dissipation from our batteries and the grid. The simple calculation on this page shows that our results are within a tolerable error. Hey guys, I'm Will.
I'm Chris. Thanks for watching our video. Please feel free to send us an email regarding our project, and we'd be happy to answer your questions.